Good morning. This is Professor Todd Elliott, and today we're going to look at the ripple on the capacitor filter. Okay, this is a bridge rectifier, and we have the 5.6 k ohm as the load, and the output here is going to be full wave. And what we want to do is to add a capacitor right there. We're going to use a 470 microfarad, microfarad capacitor to put it right here in parallel with the load. And what that will do is that will increase greatly the DC output voltage, and it will also prevent the output from going to zero at the zero crossings. Okay. All right, so let's switch over to here. Okay. Now what I've done is before I set this up, I guess I could have changed the drawing, but I didn't. Um, anyway, I decided to use the half-wave rectifier because it's a little more stark in its in the effect on the capacitor filter. Because with the half-wave rectifier, then for half the AC cycle, then the output is zero. And you can see here we have a positive output voltage, right? So it's a positive filter, positive DC output. So during the negative half cycle, then the output is literally zero, right? Now with the using the capacitor filter, instead of the output going down like this, it's going to go down just a little bit, and it's going to be held up by the capacitor because the capacitor is going to charge during the positive half cycle. During the negative half cycle, it's going to discharge, and it's going to be charged again at the next cycle, start of the next cycle. And it's going to provide a much smoother DC output. The same thing happens with the bridge rectifier we started off with, and the output will be that much better, have a much lower ripple because the capacitor doesn't have to work as hard. But this will show it quite nicely. So notice here we have the output frequency, line 60 hertz. The peak output is about 19.6, so almost 20 volts coming from a 12-ish volt transformer nominal. The mean, that's like the average here. So that would be the same number essentially you would get with your multimeter connected across the load, but set to DC volts. The scope has the ability to do that, so I decided to use the oscilloscope. And it's very much lower because this is all in the middle here is all zero. Okay, so the half-wave rectifier has a very low final DC output. So I'm going to now connect up a 470 microfarad capacitor in parallel with the load. It's an electrolytic, so we got the correct polarity. Notice now it looks like a flat line, okay? But because we have it on a very large volts per division to see the full output, but we want to look at just the ripple. We need something much smaller, so I need to change the vertical scale down. If I turn it the right way, down to, I don't know, we'll see, maybe 2 millivolts or so. We're going to flip the coupling, put it to AC so we can see the ripple. And that's got to be something like that. We'll play with the trigger because it's going to be way out of whack now. Get it down there. And it's still a little bit jittery, so we're just going to hit run stop and freeze that. Okay, so first thing you're going to see now, we're just looking at the tops of the waveform, which is kind of like ripples on a pond or on a lake on top of the body of the water. That's essentially what the ripple is. And so I've set my scope up to do the max, which is the positive peak, and the min, which is the minus peak, and not going to be exactly symmetrical. It's a real world circuit. So we have about 78 millivolts on the peak and about 59 on the minus peak. So if the difference between them, which is literally the ripple, so 78.4, 78.4 minus 59, or minus 59, minus 59.2 is about 138 millivolts peak to peak, okay? And it's always expressed in peak in peak to peak, okay? And anyway, I couldn't get the on this the uh, cursor measurements to work out correctly, so it's measuring something different than I think it is. So just ignore this. This is correct. By the way, the calculated voltage, ripple voltage, is about 120 millivolts, and we're at 138. So we're very much in line with that. Now I'm just going to take out the 470 microfarad. I'm going to chuck that over there, and I'm going to put in something. If I can read this, looks like it's 10. So something very, very much smaller. And I want you to see the effects of that. Okay, I better take my run stop off the scope, and I'm going to have to then change my vertical scale. Okay, looky there, right? The ripple has massively increased. Okay, so now we're down to, right? So this 2.1 volts, that's the positive peak. The 2.2 is the minus peak. Take the difference between the two, so 2.12 minus 2.2, okay, is 4.3 volts. So that's on top of the basically 20 volt output, peak output. Why is that so much higher? Well, because I put a very small capacitor in. Okay, you wouldn't use a capacitor 10 microfarads for a real power supply. It's way too small. But I want you to see the effect of that. The larger the capacitor, the less the ripple, which is generally desirable. There's a limit, though, of course. If you make the capacitor too big, the half-cycle surge current, when you energize the supply, will blow the diode. There's a data sheet spec for that. Um, and so a lot of power supplies, they have what's called a surge resistor, sort of in series between the rectifier output and the load. And that will limit the surge current. But anyway, you can see the effects quite dramatically. So anyway, I hope this was useful, and we'll talk to you sometime. Cheers. Bye.